Alright, hello everybody. Sorry it's been a while since I made my last video. I've just been sort of settling into college life. I just started college, which I guess might be a surprise to some people. But yeah, anyway, let's get right back into manifolds. So here, today we're going to be talking about mappings, so functions from one manifold to another manifold, and tangents. These are two very obviously important topics to talk about. So first thing we're going to do is just set up our manifolds. So we're going to let M be an M manifold, so its dimension is M, with charts UX. So a chart is going to be consisting of an open set U, which is identifiable with Rm, and our coordinates on that chart are going to be denoted by the letter X. And then N is going to be an N manifold with charts V and Y. And here V is going to be identifiable with Rn. So obviously, right, M and N have, well, for one, they have set structures, so we can define functions between M and N in the obvious way, since we know how to deal with functions of sets. And since they're also topological spaces, then we can talk about, sort of continuity of a function from one manifold to the other in a general topological context. However, since M and N are sort of, right, they're sort of Euclidean spaces like patched together, or what we would say they're locally Euclidean. And so what this allows us to do is essentially, right, and a lot of calculus ideas only care about sort of points sufficiently close to X, right? Which is a topological idea, but in analysis we sort of quantify it with, sort of epsilons and deltas and that sort of thing. And so since M and N are both locally Euclidean, and calculus ideas only care about locality, then we can generalize this to manifolds, and so we can define sort of differentiability of functions from one manifold to the next. So we will say that f as a function from M to N is smooth of smoothness class K if for all P and Q for which YQ beta of XP equals F of XP beta Q, then the functions F beta Q are smooth of smoothness class K. So essentially what this definition is saying is that if we look at essentially we're looking at charts UP and VQ, right? So UP is a chart in M and VQ is a chart in N. And so essentially what we're doing is restricting our function f to a function from Rm to Rn. And furthermore, what we're doing is sort of breaking up this this function into sort of n functions from Rm to R. And then we can define, this is the context in which, in a multivariable analysis class, you would define sort of differentiability when you're mapping into R like that. So that's how we define smooth. Oh, in smoothness class, K means K denotes how many times you can differentiate and still have, you know, like continuous functions. And so essentially from now on, smooth will essentially be the minimum smoothness class required. So technically, some people stick with the definition that a smooth function is where you can infinitely differentiate, right? It's like e to the x or polynomials and stuff. You can infinitely differentiate and still end up with continuous functions. But here, when we say smooth, if we say smooth and we're talking about theorems that involve like one or two derivatives, then we only are placing the assumption that, you know, it's if you need two derivatives, then we're only placing the assumption that it's smooth of smoothness class 2, right? We just want to ensure that those derivatives we're taking are continuous functions. All right. So the next thing to talk about is when are two manifolds considered to be equal, right? Because with the way manifolds are defined, right, they're sort of, okay, you know, we're taking you know, like sections of real, like open sets in real in Euclidean space and sort of patching them together. But you could patch things together in any number of ways. So how do we ensure that we have the same manifold, at least up to like local structures that we care about? And so this is answered with something called a diffeomorphism. So we would say M and N are diffeomorphic if there is a bijection f from M to N which is smooth of smoothness class K at least 1, right? So what this is saying is that the bijection is at least differentiable, and this seems like a weaker condition than, say, like a homeomorphism, where you have to require that both f and its inverse are continuous. But the differentiability here really is much stronger than continuity, and so it sort of implies that you have that backwards condition. And so another way of saying this is that all Jacobians, which are the determinants of partial derivatives of one coordinate, partial derivatives of the other coordinates, are never 0, right? And so this Jacobian, right, is really encoding information about the differentiability. And since it's not 0, that means we can take the inverse Jacobian matrix, which is also encoding differentiable and continuous information about the reverse direction. Now we're going to talk about some special cases of mappings. So if n is greater than or equal to m, so if n has a higher dimension, we say m is immersed in n if there is a smooth map f from m to n such that all Jacobian matrices have full rank m, right? So the Jacobian matrix in this case would be an, let's see, if it's mapping from m to n, it would be an n by m matrix. So since m is the smaller number, that's the highest that the rank can be. And really this definition is kind of weird. Immersions are better understood when you can describe it in terms of the tangent space, which we're going to define later on. So I might as well say this here. In other words, the tangent space mappings Txm to Tf of x n are injective. And furthermore, an injective immersion. So here the map F that we're defining is called an immersion. An injective immersion is called an embedding. And so, sorry, I spelled that wrong. Embedding. And so what this is saying is that both the map F and the induced tangent space mappings are injective. And this allows us to say, thus, M is diffeomorphic to f of m, which is a submanifold of n. So we can essentially say that M is a submanifold of n, up to a diffeomorphism. All right, so that concludes what we have to say about mappings. Now we can talk about tangents, another really big important topic. So let's say we have a curve x, which is parameterized by some parameter tau, which we'll let run from A to B. And so this is on our manifold M. Then in any particular chart, right, we can break this parameterization into the coordinates on UP. And so we have m different parameterized coordinates, right? And therefore we can define, since the x alphas are, these are going to be functions from real to real, so we can define, right, sort of, so I'll write it like this: tau x1p of tau d tau xm p of tau, right? So we can define a velocity, right? And here this dot is sort of standard, I guess more so physics notation for like time derivatives, or just typically parameterizations derivatives. So I'm going to be using that, but I just wanted to write this d tau to make sure that was clear. Now on an intersection of charts, these velocities have to be the same, right? But they're going to be represented in sort of different vector spaces. And so what that means is that, not that the tangent vectors have to be the same, but we can essentially parameterize when we have an intersection, we can parameterize one of the coordinate systems by the other. And this has to give us, and so essentially what we're saying here is that, okay, we have an intersection of charts, and we have some curve, right? And so here, let's say this is UP and UQ. And so here, in UP, sorry, or on this intersection, we can say that the UP coordinates are a function of the UP or UQ coordinates. But the UQ coordinates can be parameterized by tau because they're on the curve. But the UP coordinates are also parameterized by the curve, and it shouldn't matter which way we parameterize. So we should have that these two parameterizations are equal. And so now, if we take a tau derivative on both sides, we get that x alpha p is equal to d tau of x alpha p of xq tau, which is going to be, let me think. So we would have xq prime times x alpha p of xq. And so this expression, what this is going to expand out as is going to be a sum over beta, which is going to run from 1 to m, of dx alpha p over dx beta q, times the components of x dot beta q. So essentially this is saying, okay, right, we're taking the velocity, right, is like a dx over dt, and so if the x's are different, then we're going to get different velocities component-wise, but they should still represent the same change on the manifold per unit tau, right? So we have this transformation rule which relates the two ways that we're calculating the velocity. All right, and so this is showing an explicit sort of example of what a tangent vector is. So a tangent vector is a more general object. So a tangent, and they're typically denoted like this, is an object at a point X on our manifold, such that, or I should say, with components on a chart. So when we are given coordinates for x, then we sort of can find coordinates for our tangent, and on an intersection of charts, then we have a transformation rule. Which is the same as above. And this partial derivative is evaluated at our point x. Beta q. So the collection, so tangents are objects that are specific to a point on our manifold. So the collection of tangents at x is the tangent space Txm. And this is a vector space, so a linear algebra vector space. And we can sort of endow a natural basis for this vector space, which is that of the derivatives with respect to coordinates, right? So essentially what this is saying is, like, say you have, right, so a point x on our manifold is going to be locally Euclidean, so we can look at it sort of like a flat plane, I guess in the two-dimensional case. And what the tangent vector is saying is, if we say it's like 2, 1, then this is saying like 2 times the derivative in one direction plus 1 times the derivative in the other direction. And so it's essentially saying, you know, like, how much is this tangent vector going to move you along, right? Because tangent vectors are sort of related to like initial velocities of a curve. Well, that's how we sort of derived them. And so this is saying, like, you know, how fast you're going to move if you moved along this tangent vector. And so because our basis is the partial derivatives, which are coordinate specific, this is why we get different results if we use, if we are looking at one chart versus the other. And so really the transformation rule for vectors, so the transformation rule is really just a change of basis calculation. So this isn't really anything particularly fancy. or like calculus related. I mean, it has derivatives in it, but this is just a change of basis, like a just strictly linear algebra concept. Now, one last thing I want to mention, since I mentioned it on the previous page, is that when we have a smooth map, so this is smooth, this induces linear maps F star, which are linear maps from the tangent space at x to the tangent space at f of x. And the matrix representation of and so I say maps here because we have a map for each tangent space, right? So for each point x. So really, I guess I should denote this like fx star, right? The matrix representation of fx star, is the Jacobian matrix df dx evaluated at x. So this again relates sort of a calculus idea, which is also a linear algebra idea since it's a matrix, to this linear algebra idea that it's a linear map of vector spaces, but it's also calculus related. So here we can see sort of that the structure of manifolds is both heavily linear algebra related and calculus related. So that's it for this video. I'm going to try to put out, be more consistent with my uploads. So I hope to see you in the next one.